Good morning, students. Today we'll discuss embedding lemma. In order to discuss embedding lemma, we discuss some basic definitions. So the first definition is distinguish points. If we are given a collection of functions defined on a topological space, then when we say that the family distinguishes points. So let us take a topological space X top and a collection Bx. This is the collection of functions defined on X. We say that this family distinguishes points if for 2 points x and y belonging to X with x not equal to y, there exists a function belonging to the given collection of functions such that the image of x under the function h is not equal to image of y under h. It means for 2 distinct points there should exist a function from the family of functions such that the images of distinct points are different under that function. Then we say that this family distinguishes points. Next definition is this family distinguishes points and closed sets. To define this, let us take a topological space X top and Bx is the collection of functions defined on the topological space X. We say that this family distinguishes points and closed sets if for given a point x and a closed set k contained in X with x doesn't belong to k, there exists a function g belonging to the family such that image of x does not belong to closure of image of k. So if this condition holds, we say that this family Bx that distinguishes points from closed sets. Now next to define evaluation map. Let us take a topological space X top and Bx is the family of functions defined on the topological space X. For each f belonging to this family of functions, let us denote zf be the codomain of the function f. It means f is a function from the topological space X into the coordinate space zf. Zf are the coordinate space of the product space z. Z we have defined by product of zf by taking f from the family of functions Bx. By definition, the elements of z will be of the form of product of zf, where these zf belongs to the coordinate spaces of z for every f belonging to the family of functions. Now we define the evaluation map E from X into the product space z by taking an element x from here and f belonging to family of functions. Now f belonging to Bx, so f is a function from x into the coordinate space zf, and therefore f of x belongs to this coordinate space zf. So we can define zf is equal to fx, and therefore we can take z by taking the product of such coordinates. We can define z is equal to product of zf where f belonging to family of functions. Now because zf is f of x, so we can write z is equal to the product of f of x where f belonging to the family of functions. So in this way we have defined the mapping E of x is equal to z. This map is called evaluation map. Now next there is important lemma which is called embedding lemma. So firstly, the statement of embedding lemma: if we have the topological space X top and Bx is the family of functions defined on X, for each f belonging to this family we have defined evaluation map which I discussed already. E of x is equal to z. Then we have to prove that this evaluation map is continuous if and only if each member of the collection Bx is continuous. In the second part, we proved that E is 1, 1 if and only if the family Bx distinguishes points. In the third part, we will discuss E from X into E of X, that is open if the family distinguishes points from closed sets. In order to prove the third part, we will require the defining base and subbase for the product topology on Z. So let us define alpha star, the collection of all those subsets of Z which are of the form of product of BF, where this BF is equal to ZF for all except one F, and for that F, BF is open in ZF. And let us define beta star, the collection of all the finite intersections of members of alpha star. Then alpha star is the defining subbase for the product topology on Z, and this beta star, that is a base for that product topology on Z. Now first of all, let us discuss the first part. In the first part, let us take for f belonging to the family of functions the fth projection Pf, that is defined from the product space Z into the coordinate space Zf. Let us define this projection map by taking Z an element from here, and we define the image of Z under this fth projection is defined as the fth coordinate of Z, that is denoted by ZF. Now E is the mapping, evaluation mapping from X into Z, and PF is the fth projection map from the product space Z into the coordinate space ZF. So the composition of the mapping PF and E, that is a mapping from X into ZF. Now we claim that this composite mapping is same as F. So let us take an element X from here and we find its image under the composite mapping. So by definition of composite mapping, this will become PF of E of X. Now by definition of evaluation map, E of X, that is Z, so this will become PF of Z. Now by definition of fth projection map, this is the fth coordinate of Z, so that will become ZF. And by definition of evaluation map, ZF is F of X. So we have proved the composite mapping PF of E is equal to F. Now by using this, we will discuss the first part. In the first part, firstly we suppose that the mapping E, that is continuous, and we claim that F is continuous. Now we are given E is continuous map and PF is projection map, and projection map is always continuous, and composition of two continuous functions is continuous. So we can say that PF of E is continuous map, and we already discussed PF of E is equal to F. So we can say that function F is continuous. F is arbitrary member of the collection Bx. So we can say that every member of this family is continuous. Now in the converse part, we are given that each member of this family is continuous, and we claim that the evaluation map E is continuous. Now because the composition of PF and E, that is equal to the mapping F, and F is continuous map, so this composite map is also continuous. Also PF is continuous, and therefore we can say that evaluation map E is continuous. So this proves first part of embedding lemma. Now to discuss the second part. In the second part, we are to prove that E is 1, 1 if and only if the family of functions distinguishes points. So first of all, let us take the family Bx distinguishes points, and we claim that the mapping E is 1, 1. So let us take two distinct points X and X star from the set X. Now we prove that the images under E are also different. Now by definition, image of X under E, that will be of the form of product of ZF, where ZF is equal to F of X, and F belonging to the family of functions. And also E of x star, that will be also of the form of product of zf star, where zf star is equal to f of x star for f belonging to the family of functions. Now because this family of functions distinguishes points, so there will exist a function belonging to this family under which image of x and x star will be different. So we can say that for the member G, g of x is not equal to g of x star. So by definition we can say that image of x under E is not equal to image of x star under E. So different points have different images. So we can say that the mapping E is 1, 1. Now in the converse part we are given that evaluation map is 1, 1 map, and we are to prove that the family Bx distinguishes points. So let us take 2 points x and x star belonging to x such that these 2 points are distinct. Now because E is 1, 1, so distinct points will have different images under E. So we can say that E of x is not equal to E of x star. Now by definition of evaluation map, E of x is of the form of product of ZF, where f belongs to the family of functions and these ZF are of the form of fx type. So we can say that because Ex is not equal to E of x star, so there will exist a function belonging to family of functions such that Zg is not equal to Zg star. So we can say that Gx is not equal to Gx star. So the family distinguishes points. Now in the third part we are given that the family Bx distinguishes points and closed sets, and we are to prove that evaluation map E from x into E of x, that is open map. A mapping is open if image of every open set in domain is open in codomain. So let us take an open set V which is subset of x, and we are to prove that its image is open in E of x. In order to prove E of V is open, we are to prove that it is neighborhood of each of its points. So let us take an arbitrary point Z star belonging to E of V. We are to prove that E of V is neighborhood of Z star. Now because Z star belongs to E of V, it means image of V under E. So by definition of image, Z star will be of the form of image of an element of V. So there exists an element x star belonging to V such that Z star is the image of x star under E. Now by definition of evaluation map, this Z star will be of the form of product of ZF star, where this f is belonging to family of functions. Now let us take K is the complement of V. Now K is closed, and because V is open, so K will be closed, and because x star belongs to V, so we can say that x star does not belong to K. Now we have a point and a closed set such that the point doesn't belong to closed set, and the family distinguishes points from closed sets. So by definition we can say that there will exist a function belonging to the family such that g of x star does not belong to g of k closure. It means g of x star belongs to the complement of gk closure. Let us denote this set by bg. Now g of k closure, that is closed, so its complement will be open in zg. So we can say that these bg, they are open in zg. Now let us define a set B of the form of product of bf, where f are belonging to the family of functions, and for f not equal to g, the coordinate sets bf are of the form zf, and when f is equal to g, then that is defined by zg minus closure of gk. Now by definition we can say that this B belongs to the defining subbase of product topology of Z. Now, because defining subbase is a subcollection of topology, so we can say that alpha star is contained in tau star, and therefore we can say that beta star, that is also a member of tau star. So now let us define G by taking the intersection of B with E of X. Now G is open in E of X. Now we claim that Z star belongs to G is contained in EX. So firstly, let us prove Z star belongs to G. In order to prove that Z star belongs to G, we have to prove that Z star belongs to B as well as E of X. Now, because Z star is of the form of E of X star and E of X star belongs to E of X, so we can say that Z star belongs to E of X. Now it remains to prove that Z star belongs to G. Now by definition, Z star is of the form of product of ZF star, where F belongs to the family of functions and G of X star belongs to BG. The value of BG is ZG minus closure of GK. So we can say that Z star belongs to B, and therefore Z star belongs to B as well as EX implies that Z star belongs to the intersection. So we can say that Z star belongs to B intersection E of X. Now this is G, so we can say that Z star belongs to G. Now it remains to prove that G is contained in E of X. Now to prove that G is contained in E of V, it remains to prove that G is contained in E of V. To prove this, let us take an arbitrary element from G and we will claim that that belongs to E of V. Now let us take Z belonging to G is an arbitrary element. G is B intersection E of X. So by definition, Z will belong to B as well as E of X. Now because Z belongs to E of X, so by definition of image of X under E, Z will be of the form of EX, where this X belongs to the set X. And also by definition of evaluation map E, Z is of the form of product of ZF, where F belongs to the family Bx of the functions and ZF is F of X. Now from here, because Z belongs to B, therefore the gth coordinate of Z, that will be belonging to ZG minus closure of GK. It means ZG does not belong to GK closure. Now GK closure is closed, so we can say that ZG does not belong to GK and ZG is G of X, so we can say that G of X does not belong to G of K. So from here we can say that X doesn't belong to K. It means X belongs to complement of K, it means X belongs to V, and therefore E of X belongs to E of V. Now E of X is Z, it means Z belongs to E of V. So we have proved that E of V is neighborhood of Z star and Z star is arbitrary point of E of V. So we can say that E of V is neighborhood of each of its points, and therefore we can say that E of V that is open. So we have proved that image of every open set is open, and therefore by definition of open map we can say that the evaluation map E is open map if the family distinguishes points and closed sets. So this completes the proof of embedding lemma. This lemma is important lemma to prove the embedding theorem. So tomorrow we'll discuss embedding theorem.